Newton's third law is one of the most counterintuitive laws of Newton's laws. So Newton's third law is commonly stated as every action has an equal and opposite reaction, but I very much dislike that statement. I much prefer thinking of it as every force has an equal and opposite force. And another longer way to say that is when two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. So every force will have an equal and opposite force. The main reason why I dislike equal and opposite reactions is because we don't have equal and opposite reactions in the way we think of it. For most of us, an equal and opposite reaction would mean that the objects have the same motion, such as this. But that's not the case. So what actually happens is a bit lopsided. The smaller object will move further and the larger object will not move as far. They still have equal and opposite forces acting between them. I observed this at a swimming pool with my young children this past summer. My child, who's 4 years old and very light, swimming around in an inner tube, came up to me, and I was also sitting in an inner tube, and my child pushed against me as hard as they could, and they wound up moving backwards quite a ways, and I moved forwards only a little bit. So the actions and motions are not the same, even though the forces are indeed the same. And on the next slide, we've got a short video to show that the forces are indeed the same. Okay, so here we have two identical spring scales. They measure the amount of force in newtons when you're pulling on it. So they are the same size, same type of spring scale, and they have the same scale on it here. And I have Sigmund, my helper, and he's going to help me pull on the spring scales. So let's hook them together. All right, Sigmund, can you take one end, please? Take one spring scale. Hold on to the end of it. There you go. Oh, wait, don't pull it off. There you go. So now we're gently going to pull on it. So pull a little bit. Stop. Stay there. And you can see that they both say about 4 newtons. Now I'm going to pull a little bit harder, okay, Sigmund? So don't move. Alright, so I pulled a little harder, and now mine says 6 newtons, but Sigmund's also says 6 newtons. So here we're showing that the forces are equal and opposite, right? So now, Sigmund, you go ahead and pull a little bit. Right, same thing, right? Sigmund pulled, and it's the same thing over here. This is about 5 newtons, and this one says also about 5 newtons. All right, thank you, Sigmund. Good job. So Newton's third law says that every force has an equal and opposite force. So that means Sigmund is pulled down to the earth by gravity. So we can accept that. We've felt the earth pulling us through the force of gravity. But Newton's third law says that Sigmund also pulls the earth. And not only is Sigmund pulling the earth, but Sigmund is pulling with the same amount of force as the earth is pulling on Sigmund. So how is that possible, and why doesn't the earth move? So if we compare ourselves to the earth, The Earth is so much more massive than we are. The mass of the Earth is so much greater compared to us that the reactions, the actions, the motions are never ever going to be the same. So the Earth is pulling us down and we are pulling the Earth up because our masses are so different. The accelerations must also be very different in order to account for that. So while we have a very small mass and the Earth has a very big mass, we must have a very big acceleration and the Earth has a very tiny acceleration. So why doesn't the Earth move? Why don't we notice it move? It's because the Earth moves so much smaller compared to our motion that we don't notice it. And in another video, we'll do the calculations for how much the Earth actually moves when we fall towards it. But it's so small that we can safely ignore it in just about every situation. So if every force has an equal and opposite force, how does anything move at all? So for example, if we have Sigmund pushing against a wall, and we've done this a few times too, we've pushed against the wall and nothing has happened. We can push and push and push and we won't move and the wall won't move. But that is not because of equal and opposite forces. That is not because of actions and reactions. That's because we have friction beneath our feet. So if you've ever done this on a smooth floor, you may have gotten a different result, especially if you did it on a smooth floor with socks on. So Sigmund pushes on our wall. That's a force. And then the wall pushes back on Sigmund an equal amount, but in the opposite direction. And that's Newton's third law. But at Sigmund's feet, there is also the force of friction. So because we have the force from the wall and the force from friction, our net force is actually 0. And since Sigmund wasn't moving before, Sigmund also doesn't accelerate. But let's change this situation. Let's put ice beneath Sigmund's feet. So we remove friction. So now, when Sigmund pushes against the wall pushes back against Sigmund, and Sigmund will accelerate to the right. If you have ever been at a skating rink, then you will have experienced this, or go to a skating rink and try this. Push against the wall and see what happens. So now, just to write this out again, our net force is from the force of the wall pushing against us, and because this is not 0, we wind up accelerating. So we have a net force in this situation. So let's talk about some action-reaction pairs, as they're commonly called. So what is the reaction force if we mention some force? So let's take an example of the inner tube pushing against Sigmund. What is the reaction to that force? The reaction to the inner tube pushing against Sigmund would be Sigmund pushing against the inner tube. So when we have an action-reaction pair, we should only mention 2 objects. So in this case, it's the inner tube and Sigmund, and then Sigmund and the inner tube. What if we make it a little harder? We say, What is the reaction to the Earth pulling Sigmund into the inner tube? In that case, I'm being a little tricky by mentioning 3 objects all at once, but let's try to think about what 2 objects are really interacting with these forces. So, what is the reaction when I say that the Earth is pulling Sigmund into the inner tube? So we need to kind of figure out which object is not necessary. So in this case, we have the Earth pulling Sigmund. That's where we need to stop. Into the inner tube is just a little bit of extra information to distract us. So the Earth is pulling Sigmund. Let's flip that around. That means the reaction is Sigmund is pulling the Earth. So the Earth pulls on Sigmund, Sigmund pulls on the Earth. There are a few very rare situations in high school physics especially where Newton's laws don't work, and most of the time we ignore them completely because they're such specialized situations. The first is for very tiny objects, so objects that are smaller than an atom. The second is for very fast moving objects, so objects that are moving almost at the speed of light or very, very, very close to the speed of light. The third situation is non-inertial reference frames. So if our reference frame is accelerating, we call that a non-inertial reference frame, which means we are observing from a position that is accelerating. So think of some times when you can observe something from an accelerating reference frame. What are some examples of that? One example would be in a car. So when you accelerate in a car, if you have something hanging in your window, you will notice that the hanging object comes towards you as you accelerate forwards, or it swings away from you as you slow down. And it seems like something is pushing it or pulling it. That's because we are observing from a point that is accelerating, so we get some fictitious forces involved in our reference frame. Another time that it would happen is if you're on a carousel or a merry-go-round. As you are constantly changing direction by going in a circle, you are constantly accelerating because you're constantly changing direction, which means you are changing your velocity, even if you're going at a constant speed. So 2 videos that are really good at showing non-inertial reference frames. One was done by several MIT students about the Coriolis effect, and the other is the music video done by the group OK Go for their song Upside Down and Inside Out. And I'll put links to those 2 videos in the description. They're very amusing to watch. So hopefully you were taking maybe some notes as you were watching this video. And as with any subject, make sure you space your reviews of what you've learned. So in 5 minutes, take a look at your notes again and go over what we've talked about. Try to remind yourself what we talked about. What is Newton's first law? What's the second law? What's the third law? What kind of things are tricky about these different laws? And then in an hour, do the same thing. Review what you learned, try to remember what it was you learned, and then after a day, and then after a week. And if you do that, you space out how many times you revisit the material, you'll find it's a lot easier to remember and understand it. Only come back to these videos if you really, really feel that you've forgotten something important. So let's talk about what key ideas we've talked about with respect to Newton's laws. First, was forces are not needed to maintain motion. That's Newton's first law. If we have an object that is moving, it will stay moving unless there is some force acting on it already. So when we roll something across the floor and it slows down because there is already a force on it to slow it down. Newton's second law says that objects with greater inertia or greater mass need a bigger push. Newton's third law says that the forces between two objects are the same size, but they will have opposite directions. And remember, just because they have the same amount of force, that does not mean they have the same acceleration. Because of Newton's second law, force is mass times acceleration. If they have a different mass, they will have a different acceleration. And just because they may be equally opposing forces, that does not mean that they cancel out completely and our object does not move. Just like with the example of Sigmund and the wall. So one last brain teaser before we go. Is the Earth really an inertial reference frame? If we sit on the grass outside and we watch forces act and interact, are we really observing from a position that's not accelerating? When is it that we can consider the Earth an inertial reference frame, and when would we not be able to? So, did I miss something? Is there something important about Newton's laws that I left out? Are there any questions you still have? You can always leave a comment if there's something that you're still confused about. And if you like this video, be sure you give it a thumbs up and you subscribe. And join me in future videos creating a culture of discovery as we learn what the physical universe has to offer.